Hi, I am very happy to welcome you in joining this hopefully interesting conversation about one very important concept in calculus, the second derivative test. So, in order to best understand this, I'm going to go way back at the beginning of the unit of derivatives where we made the promise that we are going to learn how to use derivatives to draw graphs of functions. We started with the first derivative test. And what the first derivative helped us do was determine the intervals where the function was either increasing or decreasing. And we said that if the value of the first derivative in an interval happened to be positive, then the function was increasing. And if the value of the first derivative happened to be negative in an interval, the function was decreasing. Further to this, by knowing the intervals of increase and decrease, we were able to locate the points where the function changed from increasing to decreasing, which marked a maximum, and the points where the function changed from decreasing to increasing, that marked a minimum. So we call this finding minimum or maximum by using what we call the first derivative test, or simply by using the chart. So this very chart is what we call the first derivative test. Now in this lesson, we are going to use or learn how to use the second derivative test to determine the extrema on the graph of the function and identify those extrema as min and max without having to build this chart. Okay, so let's get started. Now, to best understand how second derivative test works, I am going to draw the graph of a function that is hosting a minimum and the graph of a function that is hosting a maximum. Actually, it would be best if we did this. So as you can see in here, at this point, this function will hit a minimum, a local minimum, and here is a maximum. So at the minimum and maximum points on the graph of a function, I want you to think about it. The first derivative will have to be equal to 0. So that's what makes them critical points. So when you look at the minimum point in here and the shape of the graph of the function where the minimum is located, you see that the shape of the graph of this function is in a cup shape. So we have a cup here. So what that means is that the second derivative of the function in this section of the graph will have to be positive. So we are going to say that if we find a critical point on the graph of a function and we find out that at this critical point, so at this particular x value, the second derivative of the function has a positive value, it means that the minimum will be, the extrema will be in a cup and it will mark a minimum. Similarly, we reason about the maximum. So we're going to say that the maximum is located at a point where the first derivative is 0. So that will give us just the x value where the function has an extrema, but we won't know exactly whether this is a min or a max unless we check the shape of the graph at this in this section. So as you can see here, the shape of the graph will be concave down. In a concave down shape, the second derivative will be negative. So what that means is that at this critical point, at this x value where the first derivative is 0, the second derivative has to be negative for this point to be a maximum. So with this in mind, then we're going to say that in order to find or identify whether a critical point represents a min or a max, then we have to use the sign of the second derivative. So the steps we follow is, first of all, we need to find f prime of x. That will help us determine the values of x where the function will have the critical points. So we do that by making f prime of x equal to 0. So that will show us where the function has the critical points or the extrema, but it won't tell us exactly whether those extrema would be a min or a max. And we don't want to use this first derivative test, the complicated chart, because true, it's not that difficult to build those charts in the examples we've seen so far, but as functions become more complicated, that can be quite a lot of work. And when we are interested in just finding the min or the max, we don't want to build complicated charts. And then we find the second derivative. Then evaluate the second derivative at the same x values where the extrema were, and then make a decision from there. If the second derivative will be positive at the extrema, that means that the critical point will be hosted inside a cup. So that means that the critical point must represent a minimum. If the second derivative is less than 0 at the critical point, x, then the critical point will be hosted in a concave down shape, which will mark a maximum on the graph of the function. So let's take a look at an example and see how we practically use the second derivative test to identify the minimum and the maximum on the graph of a function. So step number 1 would be to find the derivative dy dx. The reason why is because we need the critical point, so that would be 4x to the power 3 minus 8x. To find the critical points, we make dy dx equal to 0. So dy dx equals 0 if 4x cubed minus 8x equals 0. So let's solve. So we have a common factor of 4x, and then x squared minus 2 equals 0, which means that in this case we'll have the following critical points. One would be at x equals 0, so 4x equals 0 at x equals 0. And the others are found by making the second factor here equal to 0, which means that x is plus or minus the square root of 2. So far we have figured out that the critical points are at x equals 0, x equals square root of 2, and x equals negative root of 2. Now, we don't know whether or not they represent min or max, or which ones represent minimum or maximum. So we'll have to find out by studying the sign of the second derivative. So again, we don't want to use the first derivative, so we don't want to use the chart that indicates where the function is going up or down. So the second derivative of this function would be 12x minus 8, x squared minus 8. So then we have to find the value of the second derivative at the critical points. So what that tells us is that we need to find the second derivative at x equals 0, which would equal 12 times 0 squared minus 8. So that's negative 8, which means that is negative sign of second derivative, meaning that the function will be concave down, and in a concave down, the graph will be or will host a maximum. That's a concave down, so the critical point, the critical point will be a maximum. So let's find the derivative, second derivative at x equals square root of 2. So we'll have 12 root of 2 squared minus 8. So that would equal 24 minus 8. That would be a positive number, 16. So that means the function will be in a concave up shape, so something like this. So what that means again is that the extrema will be the lowest point in a concave up shape right here, which will mark a minimum point here. So x equals root of 2 will be a minimum, and this will be a max. And lastly, we're going to check the last point by finding the value of the second derivative at x equals negative root of 2. So that would be 12 times x squared, so negative root of 2 squared minus 8, which will also be again 16, so a positive number, so that would be a cup, which means that again the function will present here a minimum. So this is how we use the second derivative test to identify whether the extrema will represent either a maximum or a minimum. So studying the sign by studying the sign of the second derivative, which will tell us whether the function is concave up or concave down. So in a concave down again, it will reach a maximum. In a concave up, it will reach a minimum. You have another equation here that you can work on and practice. Follow the exact same steps. I hope you find this concept interesting and useful and instructions useful. And bye for now.